Okay, let's look at tutorial 2 for first law of thermodynamics, right? So I'm gonna bring you through the last 5 questions. Unfortunately, this one the video is a bit down, so no face. So you might be happy, you might say I don't know, but yeah, no face this time around. All right, so let's look at the first question, question 6 over here. Okay, when a system is taken from A to B via the path ACB as shown below, then you are given 80 joule of heat flows in the system and a magnitude of 30 joules of work is done. So ACB is through this path. Let's just mark it in red for you. So it goes this way along the path as shown. This is the first one. So in this path here, you have your Q in. Your Q in is equals to 80, and then your work on, because it's expansion, this will be negative 30. Okay. Then you are given path ADB as well. Use blue color. So ADB is this way. Okay. This one you're given the work done. So this is W on is equals to negative 10. Okay, because you both end up at B, right? Your delta U is the same whichever path you take. It's from A to B. So basically delta U of ACB is equals to 80 plus negative 30. Okay, and you will get 50 joules. Alright, then you have ADB now. Okay, so delta U of ADB is equals to Q plus negative 10, and this is equals to 50 equals to Q minus 10. So Q is equals to 60 joules, right? So that's part A. Right. Next, then you are asked to find, okay, when the system is returned from B to A along the curved path, magnitude of work done is 20 joules. Determine whether the system absorb or liberate heat. Okay, so as you go from, remember just now you go from, let's write at the bottom here. Just now you went from delta U of A to B is equals to 50 joules. That means delta U of B to A is negative 50 joules. Alright, and this is equals to Q in plus W on. Okay, and the total work done is 20 joules. Since B to A, this is a compression, so this is plus 20, negative 50 equals to Q in. So rearrange this, Q in will be negative 70 joules. Let me double check. Yep, negative 70 joules. Okay. So this is Q in is negative 70 joules. So that means heat is liberated. Okay, that means this system is giving out heat, right? So this is question 6. Okay, let's move on. Question 7. Okay, question 7 is more complex, but not too difficult as well. Okay, you have 2 moles of ideal gas. They are taken through a process. They are taken through a series of processes from A to B to C to D to A. So this is a cyclic process. Note that A to B is an isothermal process. Okay, determine the temperature A, B, C, and D. Okay, you're given the P and the V value, so that makes it very easy to do. Okay, to solve this one, let's just find space at bottom to do. So for P, let's just write here, easier to see. Okay, so to find for PA, okay, to find T, okay, we know because this is an ideal gas, we can use PV equals to nRT. Rearrange the equation, you get T equals to PV over nR. So TB is equals to TA because it's isothermal reaction. So I'm just going to use TA lah. So this is 1500. Then V is how much? V is for A is 0.05 divided by 2, 8.31. And then I'll get for A Let me just double check my answer. For A is 4510 Kelvin. That's for A. Okay. Then we can do for C and D now. Let's just go to this side here. So TC equals to P of C is 120,000 times 0.30 over 2 times 8.31. And that will give me 2170 Kelvin. You can do the same for D. So D is at 120,000 Pascal as well. 1201230 0.05 over 2 times 8.31. Then I get 361 Kelvin. Right? So this is it for the temperatures, right? Okay, maybe I just write it on the side so it's easier for me to refer later. So I'll just write it here. Let's write red here. So 4510, 4510, 2170, 361. Okay, so these are the temperatures. Okay, write down the mathematical equation involving the first law of thermodynamics. State clearly what each of the terms are referring to. So basically, your first law is delta U equals to Q plus W. So delta U gain, change in internal energy, Q heat supplied to system, W work done on system, right? So if you want to, you can write as Q in and W on, so that's clearer for you. Okay, so this is part B. Okay, next you are asked to fill up this table here. Given that delta U, Q, and W have the same meaning as the first law of thermodynamics, complete the table below. Note working must be shown clearly. Okay, let's look at this one first. Let's try to fill in as much as we can before we do anything at all. Okay, so let's see. Okay, we know that, what do we know? Okay, we can see from A to D, okay, from D to A, right? This is a constant volume change. So work done is 0. Okay, so let's write it here. D to A, work done is 0. Let's write in red color. 0. Okay, what else can we find easily? We know that A to B is isothermal, so work done is also 0. Sorry, just now the one was wrong. I realized this is wrong. Hold on. This is not here. Work done is 0 from D to A. Okay, then A to B, delta U is 0. Okay, what else do we know? B to C is also no change in volume. Okay, B to C over here, no change in volume. So again, work done is 0. Work done here is 0 as well. Okay, so what else do we know? Okay, I think that's the easy ones now. But then we can start to fill out the other things first. Okay, so right, this table we can fill out for A to B first. Let's just write that one down. A to B, because I have I need to add, I'm supposed to add W and Q to get U. So negative 520,000 plus Q gives me 0. So it means Q must be 120,000. Okay, for this to be correct. Alright. Then what else can we do easily? Let's see. Let's look at my answer key as well at the same time. Okay, no work done. Alright, we can do for DC. From C to D, we can find work done. Okay, C to D, this is a compression, so we can find work done quite easily. So let's just write it here. Okay, so maybe C to D. W for C to D is equals to 0.3 minus 0.05. So equals to 120,000 0.30 minus 0.05. And that will give me, I'm kind of jumping order, but yeah, should not be a problem. Let's see. Yeah, so that's 30,000 joules. 30,000 joules. Okay, so let's write it here. C to D, 30,000. Okay. Next, the next few is a bit more complex. Let's do for BC now. Okay, BC, right? Over here, if you want to find delta U over here, okay, we can use this formula here. We know that, okay, let me write it here in black. Okay, for BC, okay, we know that U is equal to 3 over 2 nRT. Okay, because this is an ideal gas, therefore we can say delta U equals to 3 over 2 nR delta T. And this would mean for here, this will be equals to 3 over 2 nR Tc minus Tb. And that will give me 3 over 2 times 2, 8.31. Temperature of C and B, 2170 minus 4510. Okay, so this will be 2170 minus 4510. And that will give me negative 58400 joules. Okay, so let's put this here. Scroll back up and write this here. So this is negative 58400. Okay, once you have this, you can you can find Q as well. Okay, and Q I think it's just same because it's 0 plus Q give me this value here. Okay, so Q here is negative 5400. Negative 58400. Okay. Yep. So that's it for this one. Then we can do CD as well. For CD, we can use the same way. I'm just going to do it over here as well. So for C to D, we can use delta U is equals to 3 over 2 nR delta T, which is 3 over 2 to 8.31. What's TD and TC? TD is 3612170. So 361 minus 2710 rather. Okay, and you will get this to be equals to negative 45,000 joules. Okay, so that's delta U. So once I've done that, we can go back to the top to write this down here as well. So this will become negative 4500 joules. Okay, and then once you have that, okay, I realized I wrote this work done in the wrong position. So this is work done that we calculated for C to D just now over here. This one here. So this is work done. So this one should be work done. In this case, this is compression. So this one should be here at 30,000. Okay. So now we have work done of 30,000 plus a value of Q to give me negative 45,000. So Q here should be negative 75,000. Negative 75,000. Just remove this extra joule sign. Okay, and we are almost done. The last one here, remember this column here, this delta U column, add up, it should give me 0. Okay, so right now you can see that there's negative 58400 and negative 45,000 plus 0. So right now your sum is negative 103,400. So that means this one over here, this should be 103,400. Alright, then on top here, this one, the last one here will just be 103,400, because this one, the work done is 0. So 0 plus 103,400 equals to 103,400. Alright, so this is it. Yeah, it's a bit more complex, but you realize that most of the thermodynamics first law questions are like that. Okay, next you're asked to draw the corresponding temperature pressure graph. Okay, so you are asked to draw temperature pressure graph with proper labeling of values of axis, then also draw volume temperature graph with proper labeling as well. Okay, so let's find space at the bottom to draw this. Let's go down to here. First one is temperature volume, right? Okay, temperature pressure. So let's just mark the axis first. Okay, so let's mark this axis. Temperature over pressure. Okay, let's see. We have 3 temperatures, right? 4510, 2170, Okay, so let's try. Okay, so this is let's go. Okay, 4510, erase this a bit. Sorry. 4510, and then 2710, and then 361. Okay, what the values of pressure do we have? So this is in terms of Kelvin. Pressure we have 1500250120. Okay, so 1202. Okay. So we have 120, 250, and 1500. Double check. Yep, and then okay. So if you look at this, you can find the points. So this is P slash KPA, small a, right? So you can mark the points very quickly. For A is over here. Let's mark in black color. A is at this point here. This is A. Okay. B is at 250 and 4510. So this is B. C is at pressure 120 and temperature 2170. So C is here. This is C. Okay, and D is at the same pressure but lower temperature at D here. Okay, so once you have this, you can just join in nice straight lines, which I can't draw freehand. Can go down to here and then back up to here. Right? So this is your T versus P graph. Okay, next you're asked to draw volume versus temperature. Okay, so same thing, draw the axis first. Then draw the T graph, T axis. Okay, 2 values of pressure at about two values of volume, so 0.30 and 0.05. 3 values of temperature, 361, 2170, 4510. Not to scale, just labeled lah. Okay, so let's mark the points again. A is at 4510 Kelvin, but pressure 0.05. So this is A. B is at the same temperature but higher volume. So this is B. Okay, C is at 2160 but at 0.30 meter cube. And D is over here. Okay, so same thing, join them up. And then complete this one. Okay, that's it. Quite straightforward for this one over here. Okay. Okay, so we're done with this question 7. Let's move to question 8 right now. Okay, question 8. I have a sample of ideal gas that's taken through the cyclic process X, Y, Z, X as shown. At X, temperature is 200 Kelvin. So this is, take note of some things. This is ideal gas, and they give you this cyclic process X, Y, Z, X. They tell you that point X temperature is 200 Kelvins. Okay, so calculate temperature at Y. Okay, so for this one here, let's look at how we can do this. You need to calculate temperature at Y, calculate work done from X to Y, fill up the whole table as usual, and then calculate P, coefficient of performance. This one we'll leave it later lah. Okay, so first thing first, temperature at Y. Okay, because this is an ideal gas, we can write this equation out. we can use the PV equals nRT equation again. So PV equals to nRT. If I rearrange this, I get PV over T is equals to nR, which is a constant. Okay, so with this in mind, I can say that Px Vx over Tx is equals to Py Vy over Ty. Okay, so starting on the values I know, Px and Vx is equals to Px is 1 and 2.5. So 2500 and 1.0 over 200 is equals to 7500, I think. 7500 over here. And then volume is 3. So this is 3.0 Ty. So if you solve this, Ty is equals to 1800 Kelvin. Okay, so now this is done. We can go back up to fill in the table, see what we know right now. Okay, this table now. Okay, again, let's fill in the things that are easy. Let's see which one I thought was the easiest. Okay, we can look at work done first. Work done from Y to Z. Work done from Y to Z over here. This one here is a constant volume. So work done is 0. Okay. Next, we have work done on between X to Y. Okay, X to Y can find easily because you can use the X to Y. So X to Y work done is here. This section here. This section here. This area here. Okay, so X to Y work done. Let's write it down. So this is an expansion, right? So let's write. Wxy is equals to, we use a trapezium, so this is half times 2500 plus 7500 times 2.0. Okay, and the work done here is equals to, let me see, 10,000. Yeah, so this is 10,000 joules, the magnitude. Since this is an expansion, this will become negative 10,000 joules. Okay, so negative 10,000 joules. Okay, and once you've done that, you realize that now you have delta U and W. Okay, so you can find Q. So Q here will be 40,000, because 40,000 plus negative 10,000, I will get 30,000. So this is 40,000 joules. Okay, next, what else can we find easily? We can find work done from Z to X as well. So work done is this section here. Okay, this one is easy to find. So let's just write it again over here. So WZ to X is equals to 2500 times 2.0. So I get 5000 joules. Because it's a compression, I'm going to take it as a positive value. So this is 5000 joules over here. 5000. Okay, and once we have, for this one, we have this work done and the heat supplied, I can just add them together to get delta U of negative 7500. Okay, alright, then what else do we know right now? Okay, because we know this column here, these three values add up should give me 0. So right now it's 30,000 minus 7,005, and that's giving me 22,500, and this should be 0. So this one here should be negative 22,500. Okay, because this is cyclic process, X, Y, Z, X should give you 0 delta U. So each of these terms, this 1, 2, and 3 add up should give you 0. Okay, once you have this, you can quickly complete the rest of the table. So for this one over here, for Y to Z, this is just negative 22,500 joules. Negative 22,500 joules. Okay, and once you have this, you can complete the last two entries. So again, just sum up the whole column. So for Q, 40,000 minus 22,500 minus 12,500, that will give you, how much is this? Crap. 35,000. So this is 5,000. Is it 5,000? Minus 22,000. Yeah, just sum out these three terms. So you're left with 5,000 for here. So this is 5,000. Okay, this one is negative 10 plus 5. So you have negative 5,000 joules. So you just check the last column. Q plus W, 5,000 and negative 5,000 should give you 0. Okay. Calculate work done on the gas from X to Y. You have already done that, so don't need to. So yeah, you have done that, right? Okay, calculate P. Coefficient of performance for the cycle X, Y, Z, X. Net work done by the gas. Heat supplied to gas during the change. Okay, so let's just write here lah. Net work done by gas. In the whole thing is negative. Do I start with the negative value? Just double check. Oh, I never include the answer here. Okay, so never mind. So this is negative 5,000 net work done by gas. Oh, because it's on gas, right? So this is negative. So this is just positive 5,000 here. Let me just erase this. 5,000. Erase the whole thing lah. Okay, so this is equals to 5,000 divided by heat supply to gas during the change X to Y. Heat supply to gas is 40,000. Okay, so this answer here is 1/8. So this is 0.125. Okay, that's it for this question. Okay, moving on. Let's look at question 9. Okay, let's look at question 9 right now. Question 9, you have this PV cycle within a heat engine. It's a cyclic process as characterized by rapid compression of the fuel and mixture to high pressure for greater engine efficiencies. The cycle uses the following process. A to B is a compression stroke, which is an adiabatic compression of air. Okay, so let's highlight some of the key terms first. So A to B compression stroke, which is an adiabatic compression. B to C ignition, heat addition. So this is Q in at constant pressure. And then when the fuel air mixture is ignited. Okay, next expansion stroke, isothermal expansion of the hot gases. Okay, next D to A exhaust and induction stroke. Okay, ejection of spent hot gases and the intake of the next air change into the cylinder. Net volume change is 0. Okay, so this one's a bit more complex. Let's just look at how we can do this. We're supposed to draw in the graph. Okay, let's look at this. Let's go down to here first. Okay, compression stroke. Adiabatic compression of air in the cylinder with no fuel added. Okay, so let's look at this one. Okay, let's start from one point here. Maybe just choose a nice starting point. Let's just choose here. Okay, I'm looking at answer so I know I can start from here lah. Okay, so let's choose A here. Okay, next you will do an adiabatic compression, right? So adiabatic compression will go up this way to something like this. Okay, let's just show it something like this. This is to B. Okay, then what happens at B? B to C, heat addition at constant pressure. So we add heat into the system at constant pressure. Okay, that means you're maintaining same pressure. So if you maintain same pressure, right, you add heat to the system, you're adding energy in the system. So work is done by the gas. So this one will cause it to expand at constant pressure to C. Okay, constant pressure to C. Okay, next, then what do? For D, you do an isothermal expansion. Okay, so isothermal expansion, this curve should be a bit gentler than this one over here. So bring it down to somewhere here. Okay, where to stop? Okay, because in this process, right, for D to A, right, pressure change, the volume change is 0. So it means D and A should have the same volume. Okay, over here. Okay, so D to A will come back down to here, this way. Okay. So yes, that's it. So basically, remember, if you want to compare temperatures, right, you know that because A to B is an adiabatic compression, so they definitely will have increase in temperature. I know that is larger than TA. Then since B to C is expansion, moving out, right? So this, you can say that TC is larger than TB, and then TC and TD is the same because it's isothermal change. Okay, and then the last one, TD, will definitely be larger than TA. Okay, yep, so this is it. Okay, this one is a bit tricky lah. Okay, let's move on to look at the last question, question 10. Question 10 is similar to one of the exit pass questions, right? I think. So again, we go do a bit of elimination. Alright, let's check. Okay, so which of the following sets could describe this set of changes? So you can see that x to z is z to x is a constant pressure change. So you can use that to quickly eliminate one of the answers, two of the answers actually. So this one, this p is constant. Okay, you can't really know it's constant, but you can tell that some things are not correct. So for example, obviously from z to x over here, the volume has changed. So that rules out answers, that rules out this constant volume part. So this is wrong and this is wrong. You rule out A and D. Okay, so you're left with B and C. Okay, so let's just check which one is correct. Okay, B to C compression. So for the last process, it's definitely compression at constant pressure. Okay, so let's see how we can do this. We can use the same method. We can test it again. Let's see how to explain this. Okay, let's test for option B first. Okay, so option B, let's write on the top over here. Option B. Okay, so they say that if xy is adiabatic expansion over here, that means for xy, my Q is 0. That means my delta U, and this is an expansion, right? So W on is less than 0. So delta U is less than 0. That means temperature should drop. Okay. If temperature drops and then from Y to X, Y to Z. Okay. So you're doing Y to Z is isothermal. That means temperature at Y, Ty is equals to Tz. Okay. Yep. Then you have a problem already because now you're going from, the problem comes here. Okay, you're going from now Z to X. Okay, Z to X, because it's a leftward movement, temperature should drop. Okay, so by right, your Tx should be less than your Tz. But remember, to go from X to Y, the temperature has already fallen. Okay, so you have a scenario where your Tx should be larger than your Ty already. Okay, and Ty is same as Tz, right? So these two conditions cannot be true at the same time. Okay, so Tx should be higher than Tz if that's the case. But now this is saying that, remember this leftward movement here, this will cause my temperature to drop. Okay, because I'm going for the same pressure going to a lower volume. So it should represent a temperature drop. So this is not correct. So answer is C lah, but let's just quickly check whether C is correct or not. Okay, so let's look at option C now. Let's write for option C over here. Okay, option C. Okay, let's choose black color lah. Okay, black color or blue. Okay, so option C, first one, xy is an isothermal expansion. Xy, delta U is 0. Since it's an expansion, W on is less than 0. Okay, that means temperature of X is equal to temperature of Y. Okay, and that's it. Then you have adiabatic compression. Okay, so Y to Z, adiabatic. So it's an adiabatic compression. So Q is 0. Because it's a compression, my delta U is more than 0. That means temperature of Y is less than temperature of Z. Okay, then you do a compression from Z to X. Okay, Z to X here. you do a compression, you are lowering the volume. So in this case, your Tx should be smaller than Tz, which now makes sense because remember, to go from Tx to Ty, there's no change in temperature. To Ty to Tz, there's an increase in temperature. So right now, Tz is higher than Y, which is also higher than X. Then to come back to Tx, right, it represents a drop in temperature because now you're doing compression here. Okay, so answer is C. So this one you need to like try. You usually when you face this kind of questions, right, you just need to go through the steps, see which one does not have any logical or calculation conflicts. Yep, and that's it. Okay, of course there are other questions at the back for you to try as well. If you go through this, you can go and check. There are more questions for you to do. Please try them. This chapter, like I said, is not too difficult. It's just a matter of being careful in your calculation. Usually the calculations are quite straightforward, and also be very careful about the logic as well. Okay, so hopefully when you come back in 2021, you'll be ready for the next chapter. Remember, we are not going through this in 2021 anymore. Okay, so I wish you a happy new year. Yes, and then stay safe as usual. Bye.